Test. All right. Practice exam 3. So the first one is just draw an example of each type of functional group. So there's functional groups I want everybody to know: imine, iminium, enamine, primary, secondary, tertiary amines. So just kind of some new functional groups to know: esters, aldehydes, all that kind of stuff. This is an imine, a nitrogen double bonded to a carbon. That's an imine. Tertiary amine is a nitrogen that's bonded, that has no H's bonded to it. That's a tertiary amine. And then an enamine has that double bond, that pi bond, right next to the nitrogen. Right next to the nitrogen. This is the part that's an enamine. So just kind of knowing some of those new functional groups as the key. So the next reaction asks us to draw the mechanism for the reaction below. So you should recognize this as Des-Martin periodine. If you don't recognize that, that's okay. But this is a way to take a primary alcohol and turn it into an aldehyde. So we don't have a way to do that. Actually, we have PCC does this. PCC does this, but CR, chromium, turns it all the way to the carboxylic acid. So this is just the same type of reaction as PCC as far as what we get. It's a little greener because we use a different oxidizing agent. We use this hypervalent iodide. So what happens? First step is like an SN2. This iodide has, because it's so large, has 5 bonds to it. So it's pretty electrophilic actually. So you can do an SN2 that kicks out an OAC, and an OAC is just this is an OAC right there. We just talked about this. So it makes acetic acid. So once the alcohol reacts, it can there's a deprotonation. So you make acetic acid. That's the first time you're making 2 of these. So you make 1 acetic acid here after this step. Now this step is a little more difficult. This is really it's kind of like a rearrangement. But you remember what needs to happen. You need to lose an H because you're going to oxidize this carbon. You need to take an H from that alcohol to make an aldehyde. So there's 2 H's there. I'm showing just 1. The OAC, the electrons in this bond, are going to grab the H. The CH electrons are going to make a pi bond between the oxygen and the carbon. And these electrons between the oxygen and iodide are going to go to the iodide. So 3 arrows like that. And that's kind of like a rearrangement. And it gets to, you make another acetic acid. You make the aldehyde now because there's an H here, the pi bond. And the iodine gets those electrons back. And so net what happened was the iodide got reduced, right? It lost bonds to oxygen. Iodide got reduced. This carbon got oxidized. Now it has more bonds to oxygen. And that's the Des-Martin periodine reaction. All right, number 3, just looking for mechanism arrows, just practicing those radical mechanism arrows. Right, the fish hook arrows, the single head arrows, make sure you're drawing them in with the 2 bromines. Again, be careful, draw the electrons in, show the 2 electrons in a bond, show these 2 single electrons coming together. Right, that electron, you gotta show it going to that carbon, there it is. 2 electrons coming together again, meeting in the middle to form a bond, 2 electrons in a bond. So just kind of be aware of these kind of things. We already talked a little bit about the reactivity, selectivity principle, right? Br2 is much more selective. Cl2 is much more reactive, so then it's less selective. And F2 just doesn't work. And I2 doesn't work, so it's those 2 in the middle. They're kind of the ones that work, and Br2 is the most selective of the bunch. The other thing I would add to this is just to notice, remember, right, when we make radicals, we want to make the most stable radical. So that would be the same rules we had for carbocations, we have for radicals. So hyperconjugation, so the most substituted. Pi bond resonance, lone pair resonance. So that helps you decide which CH bond maybe you're taking off to get the most stable radical possible, just like we do for carbocations. Number 4, draw resonance structures, and I change it to the least. It doesn't really matter. I just want you to see the same idea, just talking about radical stability. Just want to make sure you can do resonance structures again. Make sure you show the electrons, like the single-headed arrows, going to the bond. If you're making a pi bond, you gotta show them going to the bond. 1 electron going to the carbon, so on and so forth. Right? Make sure you have the places where the arrows go really matters. Right? Make sure they're in the right place. For when I had it most stable, it doesn't make any sense because this is secondary allylic, this is secondary allylic, this is secondary allylic. So, I mean, they're all pretty much the same stability, but this one's the least stable because it's a primary allylic, right? So less It has resonance, but it's only a primary, so less hyperconjugation. So this would be the least stable one. Make sure you can do these arrows. That's the biggest thing. Practice using those arrows. Number 5, draw the mechanism for the reaction below, and they're given the steps. Now, what I want to make sure everybody realizes, yeah, it probably will give you the steps, but maybe not for all of them. But I also don't want you just to memorize the steps either, right? So the steps are there to help you, right, to lower the barrier for some of these questions. But right at some point, I'm hoping you're starting to recognize kind of the pattern here. Also, if you're given the product, you kind of know where you're going, right? So don't forget. Obviously, these two things are coming together, right? So if you're not given the steps, don't forget to look at the products. Maybe number those atoms, draw on those lone pairs, those kind of things. That'll help you do it. But in this case, you're given the steps. So the first step is protonation, which you'd know anyways. If you see H+, protonate, 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 protonate. So protonation, that makes this carbon more reactive. We have addition, right? The alcohol. So we know we're adding this alcohol, this kind of acetal protecting group. So that adds in. We do a proton transfer. Again, careful with charge. We had over and over again, people forget to put the charges. Balance your charges. Also saw a lot of folks want to take this H and not this H. This H is attached to an oxygen with a formal plus charge. This is the more electrophilic H. If you take away this one, you get a minus charge. Should you ever have a minus charge overall? Should you have a minus charge with H plus around? Nope. So do the proton transfer with the atom that has a plus charge. Proton transfer, elimination, right? Elimination, kicks that out. Again, just following my steps. Addition, intramolecular, right? Things will happen within the same molecule faster than another one of these coming down, or water, right? In the same molecule happen faster. Addition, this makes it cyclizes things. And then another deprotonation. Make sure we have the arrows going the right way. Hydrogen doesn't want the electrons. Hydrogen is giving up the electrons. And we get to our final product. A couple of things. Balance your charges. Balance your charges. Balance your charges. If you have the steps, follow the steps. And if you don't have the steps, draw the lone pairs, number your atoms. Remember where you're trying to get to. Right? Deprotonate things with that plus charge. So circle the carbon each molecule. Below they have the most stable radical. So this is kind of another way of asking, if you had Br dot around, which CH bond would get taken off. Right, so in this case it'd be this one, not this one, because this is if you had a radical here, it'd be secondary allylic versus primary allylic. Right, pi bond resonance. This one's tricky because people see this and want to put the bromine there, but that carbon already has 4 bonds. So it's one of these 4 out here, they're all the same. And that's stabilized by hyperconjugation. Again, take away this one, because this one, if you put a dot here, it can be stabilized by pi bond resonance. This one, the one right next to the oxygen, that has lone pair resonance. Again, this is tertiary, this would be primary, so this would be more stable, lone pair and hyperconjugation. So it's just kind of like looking at it a different way. Make sure you practice this too. Alright, give the mechanism for the reaction below. So this is a Wolff-Kishner reaction, a WK reduction. At the end of the day, what does it do? Doesn't matter who the name is, that's cool. But you're taking a ketone and you're turning it into an alkane. Right, that's the net thing that happened here. We're going to add 2 H's here. We're going to get rid of 2 oxygens. So that's why it's a reduction, right? We're going to end up with 2 new bonds there, so it's a reduction. So that's the net goal. Otherwise, you've kind of seen this first step, as you've seen. Right, this is a nitrogen ketone. You're just going to make an imine, right? And tell you to make an imine. You don't have the steps given, but you know, kind of again, you know where you're going. You have H plus around, protonation always first. You see H plus, protonate. If you see base, deprotonate. And then addition, right? You've made that carbon more reactive. Add in the nitrogen piece, addition. Proton transfer, because you know you're going to get rid of water, right? You see the water's gone there. Elimination kicks that out. Deprotonation gets us to this intermediate. Now this is where things get a little different because we've been doing a lot of acidic stuff. But still, you're able to handle it because you see now basic conditions. So in basic conditions, you deprotonate first. So you deprotonate this NH. You make this resonance structure, which is good. But then we're going to ask you to do something weird. We're going to ask you to do a resonance structure that's not as good. Right? Carbon with a negative charge versus nitrogen. This is a more stable resonance structure. They both have full octets. but nitrogen's more electronegative, so it's better with a negative charge. But what we're going to see here, we know at the end of the day, we need to start adding H's to this carbon. Also, one of the products is a gas. And that's going to help drive equilibrium. Right? Even if it's unfavorable, having a gas will bubble out of the system. Draw the resonance structure, deprotonate, remake OH, or protonate ourselves, remake OH minus. So now we have an H there. We got one of our H's there. In this protonation step, we remade OH minus. So OH minus is going to do what it does. It's going to deprotonate, make another N minus. That N minus now we're going to actually do an elimination. We're going to lose N2 gas. Right? Electrons come there. The electrons go there. We're going to make it our carbanion, a carbon with a negative charge. Right? Again, being driven because we're making N2 gas. It's not there's no actually, right? Ooh. It's a one-way street, gang. All right, it's only going one way. So once we do that, we'll make that. We're going to protonate again. We're going to make OH minus. A couple things to remember and check out. Obviously, gas. Little things. I wrote OH minus as a catalyst. You're going to have to regenerate it then at the end, at least at some point. So that's why you make sure you do that too. Again, main goal was taking a ketone and adding, right, 2 H's to get that ketone to alkane. First step is something we've done. Next step is a little different, but if you know where you're going, you can hopefully know what needs to be done. So another one, mechanism for formation of product. Given the steps, again, you're not always necessarily going to get the steps, but if you have them, that's great. Make sure you follow along. Again, you've seen this a couple times. Ketone, secondary amine that you should know that makes an enamine. Protonation is first step. Nitrogen is going to add addition, made this more reactive. Proton transfer, taking the H from the positively charged nitrogen, makes this a better leaving group. Electrons come down, make sure they're going to the bond. Right, where the arrows end up matters. Elimination, lost water. Then we do this deprotonation elimination. Notice that the H plus is a catalyst. So the electrons between the CH bond go there to form a pi bond. And this pi bond breaks, goes to nitrogen. So there's no charge in the nitrogen, and we've regenerated H plus. We good on that one? Seeing none. Moving on. Going once, going twice. Last page. Last page is easy. Ish. Okay, for the last page, wants the mechanism and the products for this one. Recognize this is diball H. So you could do the resonance here, you don't have to. I showed it without the resonance. I showed it before with the resonance. Either way, it's fine. Electrons go there. Gets a negative charge on the aluminum and a positive charge on the oxygen. Even though the aluminum has a negative charge, the electron density is at the H. So it's like a hydride. Adds there. Addition. So addition and addition. We do an elimination. Right, this aluminum is going to give up those electrons. We're going to kick out that. So this is diball at the end of the day is a way to turn an ester into an aldehyde. You should just kind of know that for also knowing the mechanism. Kicks out the aluminum, and then you could draw it as this, like an ionic bond, ionic pair, O minus, aluminum plus, or you could draw them together. Either way is fine. Make sure you have the aldehyde, right? So this is another way to turn it. This is another way to make aldehydes. We talked about primary alcohols making aldehydes. This is a ester to be turned into an aldehyde with diball H. Another question, mechanism. All right, give them the product. Now we're using basic conditions, right? One of the things you first need to do is just redraw this as K plus OH minus and draw those lone pairs in. First thing you're going to do is deprotonation, right? We have a strong base. Base is deprotonate. Takes out that H, makes a negative charge there. And then that negative charge, if you look here, is just going to do an SN2. Add that on there. And yeah, this is called the Gabriel synthesis. And then you could add H plus and water and make carboxylic acids and make a primary amine. That's another way to make an amine. This is called the Gabriel synthesis. Alright, last one. Using NBS. This is NBS. This is one of the ways to add bromine. Right? So we've seen how bromine can be added a couple different ways. Way back when, HBr and alkene, Br2 and an alkene. We've seen Br2 in radical conditions. We've seen HBr in peroxides, which give us that anti-Markovnikov product. And then MBS gives us allylic bromides, bromines that are next to the pi bonds. Breaks there, makes a Br2. We're going to take to make the most stable radical. Notice the 3 arrows again. Fish hook arrows, single-headed arrows. Get the most stable radical, so it's a tertiary allylic. There's a little bit of Br2 around from MBS. Break that bond, 2 arrows come together, goes there. And we get our final allylic bromide. So NBS makes allylic bromides. You can tell radicals because you see energy or light usually. That's how you know you probably need to use fishhook arrows, the single-headed arrows.